Hey, how's it going? So this is part 2 of this lecture. I'd like to go through 2 models that show how light could interact at an interface with a material. Okay, so those 2 models, one will be similar to this guy up here, similar to this thing where we compared 2 balls as one went up a hill and down a hill and the one on top slowed down. And another one which will be finding a minimum path, a path of least time. So that one will involve turtles. So these will both be analogies, and after the analogies in the next segment, I'll explain how that works for light itself. Okay, so right now I'm just going to go through the analogies. You can see what sort of things could happen at an interface. Then we'll see what happens at an interface, and we'll discuss a little bit in that third segment what that actually means about light. Sort of like what we did in the last lecture where we talked about what light is. We'll talk about what this means about light. Okay, so in the previous section we talked about how materials move more slowly, or photons move more slowly in materials. The index of refraction is the ratio of the speed of light to the speed of the material, so it's greater than 1. The reason for that, the physical reason, was the constant absorption and re-emission of the photons as they propagate through the material. So each time a photon hits an atom, it pushes an electron into a higher shell. That excited state lasts for a little while, then it re-emits the photon. So that's more or less what happens inside the material that causes it to slow down, so that right here, they're at an equal spot. Right here, this guy's advanced a little bit, while this guy here is, because this has been absorbed by that at this time. And so you can sort of see that in that spot. So our first analogy is going to be to look at this ball, but we're going to look at it in 2 dimensions. So now we're going to have this incident ball hit this slope. So the ball is going to come this way, and this is what's happening in the x-axis up here. So it comes up this way, and it's going to bend. Its path is going to change. Whereas up here, it'll go up and slow down. It's the same thing. It's only this is the transverse component, the x and y components, and this is the x and z components. This is the x and y components. So we've got 3 dimensions. One way to look at 3 dimensions is to have 2 two-dimensional slices, and that's what we have. So the ball propagates, and as long as it's on this bottom edge, before it gets to the slope, nothing changes. The light goes in a straight line, or the ball goes in a straight line. It hits the slope, it starts to turn a little bit because it's slowing down. So I've got this as W perpendicular here because it's not really in the X direction anymore. It's in sort of the X and Z direction going up this slope. And again, this is the parallel. If this is perpendicular, this is parallel. So all that's happening is there's a little bit of a turn you might see there. And this straight line, the straight line path to the point where it hits, right, and this perpendicular line to the slope, that gives you the incident angle. That's the incident angle of this deflection. And it keeps on going, and obviously this thing curves until the ball gets up onto the top. And now this isn't going up or down anymore, so this is the x component of the final velocity, and this is the actual final velocity coming down here in the xy plane. And it just keeps on going straight for a little while longer. And again, we have a deflection angle. So we have an incident angle and a deflection angle, and there's a straight line there. Mechanically, we can figure out what this means using conservation of momentum. It's not hugely difficult because of conservation of momentum, because there's no impulse in this vertical direction. In this y direction, there's no impulse. That means there's no change in momentum there. So the momentum times the incident sine of the incident angle times the momentum times the sine of the deflection angle is equal. Because it's the same ball, the masses cancel. There's no change here. V sine theta I is equal to U sine theta d. Completely reasonable. I think you can understand that. Here, in the x direction, the difference between the x momentum and the y momentum is basically the work over the impulse. It's okay, and there should be, if I hadn't gotten rid of an m here, there would have been an extra m in here somewhere. It's all reasonably good, just work over impulse. So I think we should be okay with that. I'm not going to ask you to actually solve anything with this. I just wanted to show you that there is something that's telling you exactly how to get that theta d from what's actually happening here. But you can probably figure it out just from this. If you know v, you know u, you know theta I, you can find theta d. Or if you know theta d and theta I and your initial speed, you can find u. You can find the final speed. So it's a fairly simple way to go about things, and this is what happens in a mechanical system. When the only thing that's happening at the slope is a change in the potential energy. So that's our first mechanical analogy. We have a second mechanical analogy, and that is going to be the turtle. Okay, so the turtle has a different speed on land and water, right? And the turtle wants to get from point A to point B, and because he's an impatient turtle, he wants to get there as fast as possible. So he can go fast in the water, slow on land, and then fast in the water again. So he wants to sort of minimize that time. So if he wasn't a very bright turtle, what he'd want to do is he'd want to go in a straight line from A to B. Now, why is that not so bright? Well, he goes faster here, and he goes slower here, so he probably wants to spend more time in the water than on land, right? But because he's not a smart turtle, and somebody told him once the shortest distance between 2 points is in a straight line, he's just going to go in a straight line. That has 3 segments of equal length because of the way this is set up. 30 meters along here, 10 plus 10 plus 10, or 30 meters along here. This is just a square. So that sort of means that he has 2t here, 2 times the time in the water for either one of these, plus 1 time on land. The time in the water, going from here to here, or alternately from here to here, is found by taking this distance, which is 10 times the square root of 2, because this is a hypotenuse of this right triangle with 10 meters, 10 meters. So that's the square root of 200 meters is 10 square roots of 2, divided by the speed, which is 5 meters per second. Turtle speed in water is 5 meters per second, and that gives you 2.83 seconds, or 2 square roots of 2, as your turtle speed in the time the turtle takes in the water. Not a very long time, it's pretty close. All right, so how about on land? Well, on land, going from here to here, it's the same distance, we said, but it's about 5 times slower, so it takes about 5 times more time, which is 14.14 seconds. That means that for this straight path, you have 14 square roots of 2 seconds, or 19.8 seconds. So it's 19.8 seconds to get from here to here in a straight line. The turtle might be a little bit smarter. So a clever turtle would say, okay, I'm going to use as little time on land as possible, because that's where I'm slowest. So if I do that, then what happens is that this distance increases, and this distance goes down to its minimum possible distance, which is 10 meters. So this is a much less fun thing to calculate, right? You have 15 meters squared, which is 225 meters squared, 225 square meters, plus 100 meters squared, or 100 square meters, which is 325 square meters, which you might remember is 13/4, the square root of 10 times the square root of 13/4. Or maybe you just had to, work that out like I did. That's fine. Divide by 5, then you have 2 times the square root of 13 divided by the square root of 4, which is just the square root of 13, which is 3.61 seconds. So he's dramatically increased the amount of time he spends in the water. Before he had 2.83, now he has 3.61. That's more than 3/4 of a second. That's somewhere on the order of 1/5, I'd say 1/6 of the time that he was taking. Now he wants to get across here. And okay, I didn't have to. He gets across here. That's just 10 meters, 1 meter per second. That's 10 seconds. Not a whole lot of time. And that's 3.61 times 2 plus the 10 seconds, which is 17.21 seconds. The numbers are slightly different here because of rounding. These are sort of the exact numbers. Here I've rounded stuff out. I've rounded stuff off because you do. All right, so if you minimize your time on land, you dramatically increase the amount of time that you save. You save somewhere on the order of 15% of the journey. It's maybe a little bit less, but that's still pretty good. Now you can beat that, and to actually solve this is difficult, so that's why I'm not going to have you do that. And it gives you a quartic equation. That is an equation that's x to the fourth plus something times x cubed plus something times x squared plus something times x plus something equals 0. You can solve those algebraically if you really, really want to. They show up all the time, and whenever that happens, what I do is I ask the computer to find a number for me. And that's exactly what I've done here. And that number that I found is that to minimize the time going from here along this path, it's a 1.66 meter distance or y distance on land. That barely increases your total time on land. It's only about 1.4% more of a distance on land going from here to here, because so much of that time has to do with just crossing this 10 meters. And you reduce the amount of time in the water as well. And you don't really get that much of a gain, but you do get a gain. So part of the reason why you get such a weak gain is because of the numbers I chose, but I chose these numbers to make this one large. So this is sort of the maximum range for turtle speeds for the reference that I found. So, I put this in the computer, and it told me that the time was 17.07 seconds for this distance, which is the minimum. Actually, there's a very deep minimum, or a very shallow minimum, so there's a large range that have, to this accuracy, the same time. But in any event, this is more or less what happens if you use the least time, right? You come down here, you find a point. You find a point here that helps you minimize the time here from the extra distance, while not adding too much time here on land, too much distance here on land. And that is a minimum principle. That's something that's very deep in physics. That's something we really like in physics, is a minimum principle. And this is one other way that light might get from point A to point B and hit your eye. And so these are so this is one of the things that we found. Is we found that we have this incident and reflected angle. And if we were to look at this, we'd find that it had this exact opposite effect of what we had previously. Right over here, we had VI sine theta I equals VR sine theta R, whereas the least time has VI theta I over VI, or has sine theta I over VI equals sine theta R over VR. So the roles of the speed actually change in these two models. And in the next video, we're going to talk about the principles of light that choose between these. Is it one of these energy conservation laws? Does it have to do with the immediate vicinity of what happens to the light? Or does it have to do with the entire path, as it did in the least time scenario? Okay, so I'll talk about that next time. And why don't you think a little bit about that before you start the next video, all right? Okay, bye now.